I'm happy that we're finally at the part of the course where I get to do some lightweight coding for you, but I'm not going to teach you too much Solidity. So if you want to learn Solidity, use this website. This is great, Solidity by Example. It basically explains all the main things that you need to know. In this course, we're of course going to use Solidity, but we're not focused on Solidity. We're focused on security analysis and figuring out what can go wrong with our contracts and how people can attack our contracts and how we can attack their contracts and how to make sure that our contracts are not vulnerable to these attacks. So the theme of today's lecture is mostly about the attacks that can happen by the miners. And since I'm going to write all of this code on Remix, and this is a virtual machine, we don't really have a miner who does the attack here. So I'm going to just explain to you how the miners can attack. Okay, so let's start with a simple contract. And this is the first contract that I showed you when I wanted to talk about how smart contracts work in Solidity. And this was a puzzle, basically. So let's say I have a contract and I can pay this contract. So let's say I have a function called deposit that I can call to just pay this contract. This function is public, anyone can call it. It's also payable, so anyone can also include some money when they call deposit. And it doesn't actually do anything. So the only thing this function does is it receives some money. And remember that the money can belong to different accounts. So when I'm calling a payable function and I'm attaching some money to my call, that money actually becomes the property of the contract. So other functions of the same contract can use that money. So this function doesn't do anything much. It just gets some money. And let's say I have another function, and this is what I'm going to call claim price. The idea is that I want to set down some puzzle, and anyone who can solve that puzzle gets all the money that is in this contract, okay? So again, this one is also public, it's not payable. And let's say it gets some value X. Now the type here should be this. I'm not going to talk about the details of how types work here, just look at Solidity by Example, learn these things. The important thing is it gets some value X, and then it just computes the hash of this value. And in Solidity, again, we have a lot of predefined hash functions. One of them is SHA-256. So I want to say if SHA-256 of X is, I don't know, A, B, C, D, E, or something like that, or actually A, B, C, D, let's say. And again, I have to be careful about types, but that's not the focus of the lecture. So if I hash this X and it gives me this value, then I want to pay all the money in the contract to the person who called this function. So I'm going to say that I'm having an address payable, and this is the recipient, and this is going to be msg.sender. So whoever called this function, but I have to also make it payable. And then I just say recipient.transfer, and how much money I want to transfer. I basically want to transfer all of the balance of the current contract. And we've seen that the way we can do that is like this. So I can get the balance of this contract and I can send it to the person who solved this. Now, there is actually no point in really testing this in the virtual machine because I don't know an X that has the right hash. So I can't really do anything right now, but I can explain to you what happens here. So let's say I write this contract and I deploy it. Well, I can do at least that part. So I deploy it. Now it's on the blockchain. Now anyone can call deposit and put some money in. So let's say I want to deposit 5 Ether. I can do that. Now, as you see, the balance of the contract is now 5 Ether after this transaction. And again, all the function calls are transactions. So I'm creating a transaction that contains the address of this contract and the name of the function and the amount that I wanted to give it. So when I click here, that's what's happening there. And you can see the log of the transaction here. Whatever, this contract now has 5 Ether. Now, here's the thing. If your someone on the network who can somehow solve this puzzle and find the right value of X, then you can enter that right value of X here, and you can just click on claim price, and you should get the price. Now, in this case, as you see, the balance of the contract didn't change because this was not the right value. So I just created a transaction that sends some wrong value of X here, and it didn't pass the check in this if, and so I wasn't paid anything. But if somehow I have the right value here, then I will be paid. But that's not the main point I want to make here. So suppose I'm someone who has solved this problem and I have the right value of X. What happens if I create a transaction to actually claim my price? So I'm going to create a transaction, and what are the things that I will put in my transaction? I will put the address of this contract. I will put the name of the function that I want to call, which is claim price. And I will also have to put the value that I want for this parameter X. So I put all of these things in my transaction. Of course, I sign my transaction, all those things that we've seen before. And then I publish the transaction by just using the gossip protocol. And then I hope that a miner finds my transaction and puts it on the blockchain, and then everyone will execute it and I will get paid. That's the idea. But let's say I'm the miner and I see someone has solved this problem, and I see that there is a transaction that has the right value of X that pays 5 Ether. Why would I actually put that transaction into my block? Instead, I can create my own transaction which has the same value of X, but now the caller is the miner, myself. And then I can put my own transaction into my block. And then I'm the one who will get this money out of this contract, not the person who actually found X. So this is what we call a front-running attack. The idea is that you see a transaction that is not yet added to the blockchain, and based on the information that is in that transaction, you can create another transaction. And then you can profit by putting your own transaction before the original transaction. So the idea is that even though the original transaction was created first, and I created my transaction after seeing the original transaction, as long as I can make sure that my transaction gets on the blockchain sooner, I can profit. That's why it's called front running. It's like front running in a queue, right? And in this case, the miner can do it. So this is a terrible contract. You should never write a contract like this. So whenever you write a contract, you have to check, can I have a front-running attack? Is it possible that a miner can actually find these values? Okay, so how can I defend against this? If I want to fix my contract, how can I fix this contract? So you see, I cannot just disclose the value of X, because if I disclose X, then the miner will steal it. So what else can I do?
Maybe add another nonce.
Yes, so you can do what we did in the commit and reveal scheme. So you can have a situation where you don't directly show X. Instead, you say, I have some value of X, such that with this particular nonce, if you hash them together, you will get this particular hash. So you will show, so this is the idea. Let's say that I have my value of X, I choose a nonce N, and I compute the hash, and I know the hash of X and N is H. Okay, and then first I tell the contract that, well, I have N and H. Okay, let me maybe not use H for the hash function. I tell the contract, hey, I have a solution, but I'm not going to tell you the solution because I'm afraid that a miner would steal it. So instead, I tell the contract, here's a value of a nonce N, and here's the resulting hash. And the contract will just save that. Okay? And then I claim the price. So this is the way I would do this. So I will have first a function, let's call it commit. And this is also public. And what it gets are, well, it gets, let's say, some n, and it also gets the hash h. Okay. Now, what does this commit actually do? It's just going to save these values. Okay. So I will just have my committed values saved somewhere in my contract. So I'm going to have some value of n, or I'm going to call it committed n, and I'm going to have a committed hash. And when someone calls this function commit, the only thing that happens is that I set these values. So I say committed n becomes n, and committed h becomes h. And I have to also keep track of who made the commitment. So I create an address. Let's call this just Alice. And I say Alice is MSG.send. Okay. So the only thing that this commit function is doing is that it's saving n and h. Okay. Now, of course, I want to, in a more realistic contract, I want to have many different commitments possible because many different people might want to find a solution at the same time. But let's not think about that for now. Let's say Alice has found the solution. We can also ask Alice to put a deposit or whatever. And here I can say require, let's say I also have a Boolean. I'm just calling this one committed, it's false. And I say require not committed and make committed true. Okay, so I want to make sure that this function commit can be called only once. And when someone calls this function, they save all of these values. And I can also say that this is payable, and I can require some deposit. So I can say I require that when you're doing the commit, you're paying me some amount. Okay, whatever amount you like, so that no one just does commitments if they don't really have the solution. So now if you have the solution, you do this commitment. And then when someone calls claim price, here's what's going to happen. We're going to check that the original puzzle is solved. But additionally, I'm going to also check that this commitment was correct. So I want the hash of x and n to be h. Okay. So I check that the SHA-256 hash of x and n. I have to write some more stuff here, otherwise my type is not great, but okay. I want to check that this is h. Okay. So, and if this happens, I will not send this money to the person who actually called claim price. I will send it to Alice. Okay. So the idea here is that Alice finds a solution. She first calls commit. And basically, she's not giving the solution X, but she's giving two values, N and H. And that's enough to make sure that she was actually the person who found the solution. Later on, we can check that she was the person who found the solution, right? And we just keep these values in here. Oh, I forgot that these were supposed to be committed N and committed H, sorry. Okay, so when the commitment happens, we just save the nonce and we save the hash. And the only reason we're doing this is to avoid the front running attack later on. And then only after Alice does the call to commit and sees that this was added to the blockchain, she's now safe and she knows that she can actually reveal the value of X. Now she creates another transaction that calls claim price and gives the value of X. And if X has the right value, if it actually solves the puzzle, and if also it matches the commitments that we had before, so the hash of X and the committed nonce is the committed hash, then we pay the balance of this contract, not to the person who called this function, but to Alice. So in this case, you see that there is no possibility of front running anymore because, well, if I'm Alice and I'm doing this commitment, well, my address is going to be saved here, right? And then when I'm doing claim price, even if a miner steals my transaction for claim price and steals the value of X, it doesn't matter anymore because at the end of the day, it will be paid to Alice, it will be paid to me. So it doesn't make sense for the miner to steal it in the first place. Yes, I think you want to ask what happens if they do front running on commit. Right? Yeah, so what happens if they do front running on commit? Now we have just shifted our problem by one step, right? So if I'm the miner, I can just do front running when Alice calls commit. And then if Alice wants to call claim price later, I'm the one who will actually win the price here. So the simple answer is if Alice does the commit and if a miner does front running, Alice will simply not call claim price. And then in that case, the miner had to pay the deposit here because commit required the deposit, right? So the miner is going to lose that money. And then we can just add a time limit. We can say that if you commit and you don't reveal in, let's say, 100 blocks, we erase the commitment and then you can do it again. So that the miner just loses the money. So that's one solution here. Another solution is that in this hash here, let's not just have the solution X and a nonce N. Let's actually have the address of Alice. So maybe instead of N, let's just say that I put both N and the address of Alice. Okay, or actually, I don't even need N anymore. I can just use Alice's address, right? So, and then here, when I'm taking this hash, I have to also add Alice. You need some type conversions. Again, I would be surprised if we don't get a compiler error here, but apparently we're not getting a compiler error. Anyway, you have to make sure your data has the right type. Now, if that happens, oh, we are getting a compiler. Great. Oh, and I have typo here as well. Okay, so if you put the right data types here and you append them correctly, which I'm too lazy to do, then this would work. So here now the hash actually contains Alice's address so that no one else can really do front running on this one. So you just have to make sure that you cannot have front running on any of your different functions, or you have at least some way of defending against it. And again, one solution would be, as I said, to just include the address of Alice in this hash in the first place. The other solution is to have some time limit, and you say you commit, you have to put a deposit when you commit. And if you don't reveal within, let's say, 100 blocks, your deposit is gone and someone else can commit. You can write all sorts of code like that. But the important point, the important takeaway here is that you have to be very conscious of what the miners can do with your contract. So your contract is not just going to be executed as a normal program. Every function call is a transaction. Every transaction has to go through the miners. And the miners are really cheeky. They want to maximize their own payoff. So if you give them any incentive to cheat the system and actually steal money, they will. Okay. So now that we know this, let me show you another instance of how this interaction with the miners can actually have a lot of unintended consequences. So I'm going to create another one. Let me call this one miner.sol. Again, you have to say the version of Solidity that you're using. Let's say I want to create a contract that works like a joint bank account. Okay, so I want to have a contract called joint account. And my idea here is that I want to have two different people who own this contract, pretty much like a joint bank account. And anyone can deposit into the contract, and only these two people can withdraw. Okay, so I'm going to have two people. Let's call them Alice and Bob. I'm actually just going to use the first two accounts here as Alice and Bob. So I'm going to have, let's say, Alice, and this is Alice. So I'm hard coding Alice's address here. And let's say I also have Bob, and Bob is the second account here. I'm hard coding his address as well. Now I can only deposit and withdraw into this account. So I will just have a function called deposit again. And this function is public and it's payable. So anyone can deposit into my contract. The deposit function doesn't really do anything. And then I will also have another function called withdraw. And it takes some value X. And I want to withdraw, let's say, X units. And this is, again, public. It's not really payable. So I first have to require that the person who's calling this withdraw is either Alice or Bob. So require that msg.sender is either Alice or Bob. Okay, so if anyone else calls withdraw, their transaction will just be reverted here, and they're just wasting their gas money, because whenever they're creating a transaction, they're paying for gas anyway if that transaction gets added to the blockchain. But it has no effect because everyone on the blockchain will just run this withdraw and see that this require fails. So no one can actually withdraw except for Alice and Bob. And then I'm going to just say, let's again have a recipient, which is going to be msg.sender. And let's just say recipient of transfer. Okay. And I don't have to worry if this contract has enough balance and things like that, because if someone tries to take more than the balance of this contract, even if it's Alice and Bob, when it gets to this point, the contract doesn't have X units. And so again, the entire transaction will be reverted. We will just have an error. So I don't care about that. And so this is a very simple joint account contract. Now, what's interesting to me is this. Suppose that I put this contract, I deploy it. Okay, so this is deployed now. And let's say that someone deposits, let's say 5 Ether into the contract. So this is some account other than Alice and Bob, and it's depositing, oh, I don't know what I did there, depositing a bunch of money. And now this is Alice, this is Bob. So let's say this account, which is neither Alice nor Bob, wants to withdraw some amount. And you see that this will fail because it actually fails this require here. And actually in your requires, you can also add a message so that you can see in the log what failed. So you can say you're not Alice or Bob. And okay, let me just deploy this again. Let's deposit some amount. And let's now try to withdraw some amount. And see that there is an error. And if you go in this log, you should be able to see the error somewhere. I don't know where it is. It should be somewhere in this log. Okay. Okay, it should be in this logs. I don't know what's happening here. Again, we don't have it. I don't know. Well, the virtual machine is not really working. Okay. Or maybe I have a bug. I don't know. So anyway, you cannot withdraw if you're not Alice or Bob. You can withdraw if you're either Alice or Bob. Now, but what I want you to think about is what happens if both parties try to withdraw at the same time. So let's say I've put this contract on the blockchain, and let's say that I've already deposited some amount of money. I've deposited, let's say, 1 Ether into the contract. And now both Alice and Bob want to withdraw at approximately the same time. So Alice creates a transaction that calls this function withdraw, gives it the right value, which is like, well, this has to be in VE, so whatever 10 to the power of something, which is equal to 1 ether. And Bob does the same thing. Bob creates a transaction that wants to withdraw 1 ether. Now, let's say they publish their transactions at approximately the same time. What happens? Well, both of these transactions are going to go through the gossip protocol. They're going to make their way, hopefully, to a miner. And now let's say I'm the miner of the next block. So as the miner of the block, I get to choose not only which transactions I include in my block, but also in which order I include them. So I can decide that I only want to include Alice's withdrawal. And that means that Alice gets the money. Or I can decide to only include Bob's withdrawal, and that means only Bob gets the money. Or I can include both of the withdrawal transactions, but put Alice's first. If I put Alice's first, then Alice's function call succeeds and she gets all the money. But then later on, when Bob's function call is executed, the contract doesn't have enough balance, and then Bob's function call fails. Right? Or I can do the opposite. So basically, as the miner, I get to choose who's going to be successful to withdraw in this case, if two people try to withdraw at the same time. And that's, of course, terrible. You should not, again, write contracts that have this kind of functionality. You should not leave anything to the miners. Now, I'm going to show you that it can even get worse than that. Okay, how can it get worse? Well, as one of the parties, as Alice or Bob, you can actually bribe the miners to put your transaction first. And I'm going to show you how to bribe the miners. Okay. This course is getting interesting at this point. So let's say you're a miner. One way to bribe the miners is by just paying more transaction fee. Right? I can just say I create my function call. So here's the situation. Alice creates transaction 1, and it calls withdraw and wants to withdraw 1 ether. Bob also creates another transaction at the same time. Let's call it transaction 2. This is also withdrawing 1 ether. And now we said that they publish it at approximately the same time. But what Alice can do here is that she can include a very high gas price. Right? So we said whenever you create a transaction, you can decide your gas limits, you can decide how many units of gas you're willing to pay, and you can also decide on the gas price. You can say how much you're willing to pay per unit of gas. So one way to incentivize the miners to put your transaction first is to just give them a higher gas price. And usually most miners have this very simple heuristic that when they want to fill in a block, they just take transactions with higher gas price and they put them first. But this doesn't necessarily ensure that the miner is incentivized to put your transaction first, because at the end of the day, both transactions are going through this withdraw function and they're using almost the same amount of gas. So if you do this, you're paying a bribe to the miner, but the miner might still decide, you know what, I want to put Bob's transaction first. Okay, so we want to make sure that the miner actually has a real incentive to put Alice's transaction first. So Alice wants to really bribe the miner. Okay, how can Alice do this? Well, before this happens, Alice can first basically empty her account. So she can do a bunch of other transactions to make sure that the balance, her balance here, is very small. So let's say it's just enough to pay for gas prices. It's almost zero. Not exactly zero, but she has enough to pay for gas prices. She doesn't have any more money in her account. And then when she creates this transaction, let's say that's, and by the way, let's say the balance of the contract, balance of this joint account contract is, let's say, 10 ether. So when she creates this transaction, she immediately creates another transaction. And this is the bribe transaction. Let's call it TXP since it pays a bribe. And what it does is that it doesn't even call a function or anything in a contract. It just pays the miner. So this TXP, let's say it pays 1 Ether to the miner as transaction fee. Okay. Now, here's the problem. If Alice publishes both of these transactions at the same time, and let's say Bob is also publishing his transaction at approximately the same time, the miner now has a choice to make, right? So the miner can put Bob's transaction first, and that means that Alice will not receive any money from this contract. So then this bribe transaction that Alice is making is going to be invalid because she will not have enough money in her account to pay the bribe. But on the other hand, the miner can decide to put Alice's transaction first, which means that Alice successfully withdraws 10 Ether from the contract and Bob cannot withdraw anything. But then Alice has 10 Ether in her account, and then this transaction actually goes through and 1 Ether is going to be paid to the miner. Okay, so this is how you can actually bribe the miners to put your transaction first. And again, this is a vulnerability. You should not write a contract that has this kind of vulnerability in the first place. But if you write a contract like this is called transaction order dependence. You have a contract where the order of the transactions and the choices of the miners really matters in the result. Then you're actually making it possible for people to bribe the miners to do what they want. Okay, but I'm going to show you another version of this bribing. This is a direct bribe where Alice was actually a real person. But here's the thing. In this joint account contract, I'm saying that Alice and Bob just have some address, right? And I'm hard coding these addresses right now. And I'm assuming that these are not addresses of contracts. I'm assuming that these are just externally owned accounts that are owned by some people who have public keys and things like that. But now, let's say I have a contract where you can sign up as Alice or Bob, okay? So I say initially both addresses are 0, and I can have a function called sign up. And this is public. So anyone can sign up in this joint account. And the first person to sign up will become Alice. The second person to sign up will become Bob. Okay, so I say if Alice is 0, Alice becomes msg.sender. Else if Bob is 0, Bob becomes msg.sender. So the first person to call sign up will become Alice. The second person who calls sign up will become Bob. And well, that's basically it. Again, I have to be careful about the types. I cannot really use 0 as an address, so maybe I can convert it like this. Yeah. Again, the type conversions are really painful. That's why I say the course is not focused on solidity. I don't want to do all these things all the time. So any contract that I write in the course, you have to consider it more as a pseudocode, because I don't want to actually get into converting all these types. And when you write contracts in Solidity, you have to be careful that whenever you're doing comparisons, the types match. Okay. So anyway, now I have a joint account contract and anyone can sign up. So let's see how this works. Let me first deploy it using one of these accounts. Okay, I've deployed it. This is joint account. And I can ask who's Alice. Alice is 0. Who's Bob? That's also 0 right now. And then I can say I want this first account to become Alice. So I sign up and I ask who's Alice. Alice is this address, which is the address of the first account. And now if I use the second account to sign up, Alice doesn't change, but Bob becomes the second account. And now at this point, if I sign up with any other account, nothing changes. So Alice and Bob remains. So very simple function. The first person who calls it becomes Alice. The second person who calls it becomes Bob. And then, of course, they can deposit in their joint account and any one of them can withdraw. But the part that is interesting to me now is that, well, I'm letting Alice and Bob just be addresses. And I said that every account on this blockchain has an address. That includes the contracts. So now I can write a contract who signs up in this contract as Alice, right? So I can have another contract. Let's call this one Alice contract. So Alice actually uses her contract, let's say, to sign up instead of using her own public key to sign up. And I can just have a function here. I'm going to call it participate. This is public. The way it's going to work is that I'm going to take the address of the joint account and I'm going to try to sign up in there. So now how does this work? Well, I told you that the contracts here are pretty much like classes in Java. So if I have the code of joint account, I can just write something like this. Joint account, I don't know, let's call it A, is a joint account at this address. And then I can just call the functions. So I can say a.signup. Okay. So of course, now I have to first deploy my joint account, and then I have to deploy this Alice's contract. And then I have to call participate here, and I have to give the address of the joint account. So let's do that. I first deploy my joint account. So this is joint account, and you can see that Alice is nothing there. And then I'm going to deploy Alice's contract. Now, you see, when I deploy this contract, it has an address. And so my Alice's contract doesn't know the address of joint account. So I have to copy the address of joint account and give it here so that it's passed to this function participate. And then now I can call participate. And so when I call participate here, it used this address to find the joint accounts contract and then call the sign up function there. So now if I ask who's Alice, you see that Alice is actually this contract. So the view here is not great. So there is like CF7 at the end here. It's actually this contract. Okay, so why am I doing all of this? Well, first of all, I wanted to show you how you can actually connect two contracts together and call a function of a contract from another contract. But the more interesting thing here is that if Alice is a contract, then we can actually do nicer attacks here, and we can bribe the miners more directly. So here's the thing. I can have a function here, and I'm going to call this withdraw again. Well, or instead of withdraw, let me call it attack. And again, it has to get the address of the joint account contract. And this is also, let's say, public. Or I can just do access control or whatever. And here's what I can do. I can say, call the withdraw function of joint accounts. And of course, I need some value X. So try to withdraw X units from the previous contract, from the joint account. But after that, bribe the miner. Send some money to the miner. Now, how can I send money to the miner? Well, I can actually access the address of the miner in my code. And this is, again, what we saw last time. So if you just search for Solidity global variables, you will see this. It's called block.coinbase, I think. Yes. So it's this one. Block.coinbase gives you the address of the miner of the current block. So I can say block.coinbase.transfer some amount, some bribe. Okay. Now, here's the thing. This is how I'm going to attack. There is this joint account, and let's say someone else has signed up here, or maybe let's say Bob's address was hard-coded in the beginning. So let's say this is Bob. Okay. So I sign up as Alice in this contract, but I'm not going to use my actual public key. I'm going to use my contract. So I first publish this contract, which is just written in order to attack the previous contract. And then I call the participate function in this contract so that this contract becomes the Alice in this contract. Okay. Now, instead of calling withdraw directly, later on, I call the attack function of my Alice's contract. Now, the difference here is that this is just a single transaction. This is a single function call that calls the withdraw here and then tries to pay some amount of money to the miner. So it's doing the bribing and withdrawal at the same time. Now, if this withdrawal fails, if this contract does not have enough money to give to me, and then this transfer basically fails because the contract doesn't have enough money, then it throws an exception. But if it throws an exception, then an exception is thrown here, which means that the entire transaction that was calling the function attack is going to be reverted, which means the miner is not going to get his money. So this is, again, a contract, and I'm telling the miner, if you want to get your money, you'd better make sure that I get paid first. So I have to first be able to withdraw in order to then be able to pay you the, let's say, reward or the bribe that I want to pay you. So now, again, at this case, if there are two different transactions, one transaction is from Alice. She's creating a transaction one that is calling Alice's contract .attack. And then there is Bob who's making a transaction that is calling joint accounts.withdraw, right? The miner will always prefer to put Alice's transaction first because that's the transaction that is going to pay the miner. Of course, all of this is assuming two things about the miners, which are not necessarily true in the real world. First, we're assuming that the miners are rational in the sense that they just want to maximize their own payoff. And they actually care about this money. So if this money is not enough, maybe the miner doesn't even care about it. And the second assumption here is that we are assuming the miners are smart and they actually understand what's happening with the transactions. Most miners are not that smart. Most miners just take transactions, don't think about it, put it in their block. But assuming that the miners are smart and rational, this is a way to actually bribe the miners to put your transaction first. Okay. But actually, if I deploy these contracts, you will now see that something will go wrong. So I have to just tell you a little bit about that. So let me just do this. Let's say I first deploy joint account. And then I deploy Alice's contract. And then I tell Alice's contract to participate in joint account. And let's say I pay some money to the joint account. Okay. And then I tell Alice's contract to attack joint account. So in this case, actually, since there are no competing transactions, it should just succeed and the balance of Alice's contract should go up, right? Because Alice's contract will just call the withdraw in joint accounts and that should succeed. And of course, a little amount is also paid to the miner, but who cares about that? Let's do the attack. And here actually, oops. Oh yeah, I forgot to give the value X. Let's do this attack. Okay. Now you see that actually this transaction failed. Now the reason this transaction failed has to do with a very small detail that I have to tell you about. And it's about what happens when you transfer money to another contract. So If Alice here is just a normal externally owned account, and if your contract joint account actually transfers some money, then Alice will just have that amount added to her balance, right? But if Alice is herself a contract, like this case, when you transfer money to a contract, you actually have to call a function of the contract. You can't just transfer. What's that? Okay, I have no idea where that's coming from. Okay, we have 5 minutes remaining. I hope you don't get a headache in 5 minutes, and then we will be out. Okay, whatever. So when you transfer money to a contract, you actually always have to call some function of this contract. So that's why, for example, here I had a function called deposit, which would just take deposits, because otherwise I wouldn't be able to send money to this contract. But the default behavior is that you can do it without having a function with a particular name, and you can just call the function receive. So you can see examples of this in, yeah, oh, it went away, great. So you can have a function called receive in your contract. And if someone just sends money to your contract, it will automatically call the function receive. Okay. So this is how it looks like. You don't even have to use the word function. You can just write receive. It has to be external, which means that it can only be called from outside of your own contract. And of course, it has to be payable. So in order for this entire thing to work, my Alice's contract should also have a function called receive. I don't need to write function. And this is external, and it's payable. And again, it doesn't do anything. Basically, the idea is the same as the deposit function that I had here, except that receive is the default function that is called whenever someone sends money to this contract. If they don't specify any particular function name, this is the function that is called. Okay, but now we can have a more interesting kind of attack. So here's another idea. Let's say that I have this joint account, and let's say whenever someone calls withdraw, instead of sending the money to the person who called withdraw, it's going to send half of the money to Alice and half of the money to Bob. Okay, so I'm going to say Bob that transfer half of the balance. So address this, the balance divided by 2. And then I'm going to say send the rest to Alice. I don't have to divide by 2 anymore because this is now the remaining balance. Okay, and of course, I have to change some other things here. So it should be an address payable and so on. You get the idea. I don't want to go through the types again. So let's say I have a function called withdraw that sends half of the money to Bob and the other half to Alice, and anyone can call this function. Now, it seems like this contract is not really vulnerable to any kind of attack, right? Because, well, you can deposit in it. You have 2 owners, Alice and Bob, and no matter who calls withdraw, each of the owners is going to get half of the money. Well, it's not exactly half because this is integer division, so it might be a little bit different, but everyone gets almost half of the money. Now, what kind of attack can I do here? Actually, Bob can have an attack here. Or then let's change the order. Let's always have Alice be the attacker. So let's say Alice first gets half of the money and then Bob gets the rest of the money. Now, again, the attack that I can have here is that I can say maybe Alice is not an externally owned account. Maybe Alice is also a contract. So again, I will have a contract as Alice that I write only just to attack this contract. And here's what I do. In my receive function, I just write 1 line. And this means that it just throws an error. Or another way of throws an exception. Or I can write require 1 is equal to 0. Right? Now what happens? Now, if anyone calls this function withdraw, it first tries to transfer money to me, to Alice, as this contract. But my contract just refuses to get the money. Whenever my contract is called, whenever money is sent to my contract, the receive function is called, and it just throws an exception. And that exception is popped all the way up. So this withdraw throws an exception. So the entire transaction is reverted. So no one can get money out of this. Of course, for this to be a viable attack, I will probably have some Boolean here saying whether I want to attack or not. And then I have a function that I can use to control the value of this Boolean. And here I just say if attack, do this. Okay. So as Alice, I can just make sure that I can control when I can do an attack. Okay, and now again, we're back to the whole extortion story and things like that. So I can tell Bob, you have to pay me some amount before I disable the attack, or otherwise your money is just going to be locked in this contract. As you see, it's interesting. You can do all sorts of things here. So you have to be very careful. You have to be careful that whenever you're transferring money to someone in your contract, you have to first of all figure out if that person who's receiving the money can actually be another contract. And if they can be another contract, then you have to figure out how to defend against attacks like this, how to make sure that you are not executing the code of the other contract, because then that can attack you. We will talk more about this in the next session. Okay, so that's it for this session. Have fun, and I'll see you next week.